Module 1, Use of Manipulatives and Strategies, with a focus on fractions. This is part 1 of a 3-part professional learning session for Module 1. We encourage you to follow along and construct the visual representations discussed within this session. Feel free to pause the presentation at any point.
We are going to focus on 3 types of fraction models as we discuss the multiplication and division of fractions. The first is a set model. When using set models, it is important for students to know what defines the whole, what defines the parts, and what the fraction means. Let's look at a few examples of set models.
Take a look at this set. The whole represented here is 12. This set can be described by its fractional part. Half of the set is yellow. The set is separated into 2 parts with equal amounts in each part. Therefore, 1/2 of 12 is 6. 1/4 of the set is red. There are 3 red tiles noting 1/4 of 12 is 3. The whole was separated into 4 parts with equal quantities within each part. Consider the birthday cake task within Module 1. Students are required to use set models to determine how many jelly beans would go on each portion of the cake. Here we have 8 jelly beans. How many jelly beans would be on each portion of a cake cut into 2 halves? Remember, with a set model, the parts are defined by the equal number of objects. Therefore, each half would need the same number of jelly beans. Here, the part is 4 and the whole is still 8. This model represents 1/2 times 8, which is 4. What if the cake were split into quarters or fourths? The whole would be separated into equal parts, leaving 2 jelly beans on each slice of the cake. 1/4 times 8 is 2.
Think about this. If 12 counters are 3/4 of a set, how many counters are in the full set? Try using countable objects such as color tiles to answer this question. Moving on to length models. When using these tools, the length of the tool determines the whole, and the parts are defined as the equal distances or lengths.
Some examples of linear models or length models for fraction representation are listed here. Within this presentation, we will discuss a few models. While reviewing the number line and Cuisenaire rods, think about how the same problems can be modeled with fraction strips and/or adding machine tape. Number lines can be used in multiple ways. This number line begins with 0 and ends with 1. It has been separated into 4 equal parts, and 1/4 is represented. For this problem, we're going to determine 1/2 of 1/4, or 1/2 times 1/4. It is important to understand your whole in each situation or problem you solve. For this problem, what is our whole? If you're thinking 1, you may be expressing a misconception you have about fractions and the term whole. We're looking for the entire amount of which we want to find half. We are looking for half of 1/4, making it our whole for this problem. Using a double number line, noting they are the same length, 1/4 is cut in half. To determine the value of the cut, one would only need to divide the new number line into equal parts. Because the 2 number lines are equivalent, we are able to find equivalent hash marks on the new number line, which are aligned with the original number line. 1/2 of 1/4, or 1/2 times 1/4, is 1/8. Before moving on to the next slide, try first identifying the whole within this expression. Then, use the double number line strategy to find 1/4 of the given amount. You should have determined only 2/3 of the original number line needed to be broken into 4 equal parts. We want to find what is 1/4 of it, so we must identify where 1 out of 4 equal parts would be located. Using the double number line, we are able to find equivalent values and separate the number line into equal parts. 1/4 of 2/3 is equivalent to 1/6. Taking it a step further, let's look at finding more than a unit fraction. What do you notice about this problem? Do you think it would change your strategy at all? Notice the entire amount is only 1/3, which has been separated into 5 equal parts. 2/5 is identified, and an equivalent amount is noted using the double number line strategy. Students should have an opportunity to work flexibly with the manipulatives and decide which strategy is most efficient based on the problem they are solving. With that in mind, we will look at some of the same linear model examples being used to represent division of fractions. Similarly to dividing whole numbers, when dividing fractions, students are to determine how many groups or sets of the divisor are within the dividend. Looking at this problem, we want to know how many 1/5 are in all of 4/5. On the number line, 4/5 is represented. 1/5 is easy to identify as we are only dealing with one type of piece, fifths. There are 4 sets or groups of 1/5 within 4/5, so the quotient is 4. Take a look at this problem. Using the number line, changing the mixed number to an improper fraction is unnecessary. We are looking for the number of 2/3 within 1 1/3. Number line usage is very flexible. You can decide which numbers will be represented on your number line. Here, we have represented 1 1/3. The jumps show the number of 2/3 within 1 1/3. Notice again here, when dealing with one kind of piece, in this case thirds, we are able to easily find the groups or sets. With this problem, you'll see we aren't dealing with the same kind of piece. Here we are using a double number line to solve. Take a moment to think about how you could adjust our fractions so they would have a common denominator. Then think of how you would use the number line to solve. Here we have 2 number lines of the same length, which is very important. One number line shows the dividend, the other shows the divisor. We are looking for the number of 1/4 and all of 3/8. Using the number line, we can see there is one whole group of 1/4 and half of a group of 1/4. Therefore, the answer is 1 1/2.
Cuisenaire rods are a very flexible tool. Allow students an opportunity to explore the lengths of the rods. Students are able to decide or determine which rod will represent their whole.
The great thing about Cuisenaire rods, in my opinion, is the flexibility in showing fractional relationships or proportional relationships. In this example, the brown rod is the whole. Purple is 1/2 and red is 1/4.
For this problem, we were looking to find how many 1/4 were in all of 1/2. Remember, our red rod represents 1/4. There are 2 red rods that are equivalent to 1 purple rod, which represents our 1/2. So the number of 1/4 within 1/2 is 2. Think about this. How could you model 1 1/3 divided by 2/3? Using a length model, I want you to try to model 1 1/2 of 2 3/4. The third type of model is area models. With this tool, the whole is defined by the area of the defined region, and the parts are the equal area. The third type of model is area models. With this tool, the whole is determined or defined by the area of the defined region, and the parts are the equal area. Folding paper is a concrete way to visualize the multiplication of fractions using an area model. Begin with a whole sheet of paper. Here we have folded the paper into 4 equal parts to represent fourths. 3 of the 4 parts are shaded. Now we are representing 3/4.
The fourths are separated into thirds. We are trying to identify 1/3 of 3/4. Notice how the colors overlap. It shows what fractional part of the whole is 1/3 of 3/4. There are 12 equal parts and 3 parts are overlapping. 1/3 times 3/4 is 3/12. This same strategy works with drawings as well. What would be the next step to represent 1/2 times 1/4?
Think about this. How would you use an area model to solve 3/5 of 3/4? Abstract thinking is the last stage of a 3-stage process called CRA, or Concrete, Representational, and Abstract. With enough experience using area models or length models, students will start to notice a pattern. Present students with an opportunity such as this. Look at the 3 problems below. With these problems, students can identify a pattern by first modeling the expressions using an area model. Then ask, how did you figure out that the denominator would be 12ths? Is this a pattern that is true for the other examples?
In this example, each mixed number is decomposed into their whole numbers and fractions. The wholes are multiplied, each whole is multiplied by the other's fraction, and then the fractions multiplied by each other. The partial products are combined, because remember the mixed numbers were decomposed. Notice in this strategy we are combining a whole number and an improper fraction. The final answer is not in simplest form, but still reflects the correct answer.
The common denominator algorithm is a strategy that is not often used in American classrooms. We're going to see how this strategy connects to the visual representations that we created earlier.
Earlier in the presentation, we looked at dividing fractions with concrete materials and in representation form. Here, we are connecting the representation to the abstract. Remember, when dividing, we're looking for the number of the divisor within the dividend. For this problem, we're dealing with one size piece, eighths. Because we are dealing with the same size pieces, we are dividing 7 pieces into groups of 3. Here, we are not dealing with the same size pieces. From our visual representation, we are able to find equivalent fractions which have the same number of equal parts. We now have a common denominator. 2/3 is equivalent to 6/9. Because we are dealing with the same size pieces now, we can focus on how many groups of 6 are there in all of 4. We won't use the language "we cannot divide 4 by 6" because that will develop misconceptions. However, we realize there is not a whole group of 6 within 4, helping us reason that our quotient will be a fractional amount. Looking back at the visual representation, we see only 4 out of the 6 pieces of the 6/9 are within 4 pieces of our 4/9. 4 out of 6 can be written as 4/6 or 4/6. This can be simplified to 2/3.
The invert and multiply algorithm is the most commonly used but most commonly misunderstood algorithm for dividing fractions.
Here, we want to identify a pattern through the use of visual representations. For each problem, use an area model or length model to show the division problems. We have provided an example for the first expression. Directly next to the expression, we are using an area model. The large rectangle represents one whole. We want to determine how many halves are within the one whole. We see the one whole has 2 pieces within it. Therefore, the quotient of 1 divided by 1/2 is 2. Before moving on to the next slide, go through each expression using an area model or length model to verify the quotient. Take a moment to cross-check the patterns you identified with the ones listed here. By looking for the patterns, the conjecture can be made. The dividend can be multiplied by the denominator of the divisor, and it will result in the same quantity as our visual representation. Adding more to our conjecture, here we are looking at the number of 2/3 in all of 2 wholes. We began by creating our 2 wholes, followed by creating 3 equal parts within each whole. We see there are 6 pieces, which is 2 times 3, or the dividend multiplied by the denominator. Remember, our goal is to identify the number of 2/3 within 2 wholes. Therefore, we are separating the 6 pieces into groups of 2. Another way to look at it is 6 divided by 2. Both perspectives result in 3. So 2 divided by 2/3 is 3. Retracing our thinking, we multiplied 2 times 3, giving us 6 pieces. We divided 6 by 2 as we looked for groups of 2 within 6. The end conjecture is the invert and multiply strategy. Invert the divisor and multiply it by the dividend. This strategy is something students should have an opportunity to derive. Begin by having them look for patterns just as you did today.
What do you do when students struggle? Differentiation will play a key role in your classroom. Allowing students to work at their own pace to build their understanding will be helpful. It is okay for students to remain in the representational stage for an extended period until they're ready to move to the abstract thinking stage.
Tiered tasks are a great way to allow students to work at their own pace of understanding while continuing to move through the curriculum. You may have a single task tiered at 3 different levels: below expectation, at expectation, and above expectation. Here is an example of a tiered task. The order of tiers does not matter. We have aligned Tier 1 to above expectation, where students will work with larger numbers. Tier 2 and 3 still have the option of using understanding within the representational stage of the CRA model to solve the problem. Tier 2 must begin to bridge understanding from representational to abstract. Tier 3 is only required to use representations.
Meeting with small groups of students is certainly beneficial. We have pulled suggestions for implementing small groups. The link listed will provide insight on how other teachers are implementing small groups at the secondary level. In a 45-minute class, your small group rotation could look similar to this one.
This suggestion comes from the Social Emotional Learning and Mathematics session from Global Math Department. It lists a class size of 30 students to demonstrate you do not have to have a small class size in order to implement small group instruction. The Georgia Department of Education is not suggesting the foundations of algebra class sizes should be increased to 30 students.
This is a sample of a small group rotation for a 60-minute class.
This suggestion comes from the Social Emotional Learning and Mathematics session from Global Math Department. It lists a class size of 30 students to demonstrate you do not have to have a small class size in order to implement small group instruction. The Georgia Department of Education is not suggesting the foundations of algebra class sizes should be increased to 30 students.
The Georgia DOE has created a wiki space for high school teachers to engage in discussions about math teaching using the Georgia Standards of Excellence. Here, you'll find a forum to keep the conversation going, resources, and you might even make a few friends. It's a call to action, and you are invited to make a difference. Access this online community here at ccgpsmathematics9-10.wikispaces.com.